So, welcome again. So, in the previous class we were looking at eutectic phase diagrams, right. So, how can one just by looking at the free energy competition between various phases at different temperatures come down to a eutectic phase diagram. We started with the case where alpha is a regular solution, liquid is an ideal solution. But the spinodal decomposition in a regular solution with omega greater than 0, that's what I should have mentioned in the previous class also. So which would spinodally decompose, but the spinodal decomposition temperature is actually higher than where the liquid phase can completely disappear at all compositions, right. So if that's the case, I can form a eutectic. That is one condition to get a eutectic. Or so I can, to start with itself, have two different phases, two different solid phases, alpha and beta, right, with different sort of free energy curves. And so beta may be 2 rich, alpha can be 1 rich, right. So that's how typically things happen. And there also so I can come to this binary eutectic phase diagram, okay. And then we said the advantage of having a eutectic is that so overall the melting point reduces, right. So I can use it for applications such as soldering, or so solder alloy actually gains its prominence because it has a eutectic temperature, because it's a eutectic alloy, right. So people just say something is a eutectic alloy. This means that the melting point has reduced and it has a corresponding eutectic phase diagram, okay. So today we will start with something else, another case study. And this case study is growth of nanowires, and these are going to be single crystalline nanowires. Okay. And we are going to use the eutectic phase diagram to grow single crystalline nanowires, to understand the mechanism of growth of single crystalline nanowires, okay. And the process is called vapor liquid solid process, or so called VLS process. It's a very neat way of growing single crystalline nanowires. So what you do in this process, first let me describe what is done in this process. So you take a substrate, right, does not matter what substrate it is, but maybe to a second degree it matters what substrate it is, but substrate is just to host the nanowires. So this is what is called a substrate, some single crystalline silicon or something like that. And on this substrate what you can do is you can coat a thin film of gold, right, some 2 nanometer, let me put that in golden color or some other color. Oops. Okay, so there is some 2 nanometer of gold film sputtered. We have seen what sputtering is, right, sputtered onto the substrate, right, and you heat it up a bit, right, or you do not need to heat up. But in general, when I put 2 nanometers of gold, right, so this is the substrate, now I am taking a cross section of it and trying to see what happens in the cross section. There is supposed to be a continuous film of 2 nanometers, but 2 nanometers gold typically does not form continuous films, especially on a substrate like silicon, right. That is because silicon hates gold, in the sense so gold wants to form these droplets. Gold does not form a proper wettable surface, right. So we'll look at this in when we look at surfaces, right. So gold cannot wet silicon, right. So instead of forming a continuous film, what gold does is gold forms these droplets, okay, which do not wet silicon completely. The contact angle is quite large, right. So with a large contact angle, okay. So, in the solid phase, right. So, first I have these gold droplets, or so that are formed in the solid phase. Okay. So, this is what I start with. So, in other words, I have taken silicon and I have spread some gold catalyst on silicon, right. So, I mean they can be slightly varying sizes because I have heated a sputtered compound, right. Or I can just put some colloids of gold, that is also fine, I do not need to sputter it, or put some gold colloids using what is called drop casting. So, put this gold colloidal solution in some kind of a pipette, right, and just press this and then and then spread them around, right. So, that is called drop casting, and the solution evaporates. If you put it in some ethanol or something like that, the solution evaporates and all you have is gold colloids that are arranged in certain fashion. Okay. Alright, so I have gold to start with on a substrate. Okay. Now, to this gold I send in, right. So, I put this entire thing in a furnace, right. So, there is a source of silicon, C lane is a source of silicon, right. So, I want to grow silicon nanowires, or I want to grow any nanowires, right. So, I need to have a precursor, right. This furnace is connected to vacuum pump. Okay. So, some kind of a vacuum pump, and so it is heated up. Okay. So, this source of silicon is going, and so I put my substrate somewhere here, right. So, on the downstream this is the substrate. Okay. So, the gold is now getting the source of silicon. The gold catalyst or whatever is on the silicon substrate is now seeing SiH4, right. So, in the vapor phase, right. So, this is the precursor, C lane is the precursor. So, SiH4 is coming over gold. Okay. So, and then what happens is so magically if I do this at the correct temperature and right pressure, what I start seeing is alright. So, this gold catalyst now starts rising up, and there is a small, and if I just follow this, right. So, the gold catalyst rises up, and then there is a small nanowire whose size is determined by the gold catalyst, the size of the gold catalyst, right. So, the nanowire starts to grow, and this is a single crystalline nanowire. That starts to grow. Okay. And that is so limited, the size of the nanowire or the diameter of the nanowire is limited by the diameter of the gold catalyst. If I didn't have a gold catalyst, I would get some kind of a a surface deposition of silicon, so I mean, so I do not know what phase it is, but it is not going to form nano wire, it will form other nanostructures, right, some flakes or something like that. Okay. So, gold is catalyzing the growth of a nanowire. Okay. And so, we are going to use certain ideas of thermodynamics here. So, first I said silicon hates gold, right. Silicon does not want to form bonds with gold, and this is in the solid state. So, in solid state solubility of gold in silicon or silicon in gold is very, very less. Okay. So, in solid state, when I talk about this alpha and beta phases, alpha let us say is a silicon rich phase and beta is a gold rich phase, both of them are almost pure, right. Alpha will have almost 100% silicon, beta will have almost 100% gold, that when I draw so in a phase diagram I don't really see this alpha and beta phases. Instead of saying alpha I am just going to call it silicon, instead of saying beta I am just going to call it gold, right. So or FCC gold or something like that, right. So alpha is going to be diamond cubic silicon, okay. So alpha and beta don't so don't have any solubility of beta doesn't have any solubility of silicon, alpha doesn't have any solubility of gold, okay. But the liquid phase, however, liquid is sort of chaotic, right. In the liquid phase gold and silicon can mix to form a solution, right. So that I am going to call it gold silicon solution, then that is the liquid phase, okay. Alright, so I am sending silicon H4 on gold, right. Now silicon H4 can react with gold and then form AuSi alloy only in the liquid phase, right, not in the solid phase, right. So I have to have my temperature greater than a certain temperature T star, let us say, where gold or gold silicon melts, right. So that is where the eutectic comes in, okay. So we will look at it, right. So I have to do this process at that temperature and only then silicon can get into gold and react with gold and somehow form silicon, okay. Okay, so now let us look at the process, how it happens, okay. Alright, so first I have gold, right, and I am doing this at this temperature, right. So and this temperature you can see is less than the melting point of gold, it is less than the melting point of silicon, right. So gold has a melting point of 1064 degrees Celsius, silicon has a melting point of 1414 degrees Celsius. I am doing this process at about 700 degrees Celsius or something, which is less than, this is some random number I have just given, right. So arbitrary number, but so in general VLS is a low temperature process, okay. So I am doing this at this temperature, okay. Now at this temperature I start with pure gold, right. So now gold is solid to start with, I have sprinkled solid gold particles, right. Then I am sending more and more silicon and then you can see in this phase, this is the phase diagram, right. So this is the eutectic phase diagram. And in the eutectic phase diagram, where are the pure alpha and beta phases? The pure alpha and beta phases are almost here, right. So this is pure gold because gold does not like combining with silicon in the solid phase, and this is pure silicon, and same thing with silicon, silicon also does not like combining with gold, right. So this is pure silicon, this is like my beta phase, this is pure gold, this is like my alpha phase, okay. They have almost so the compositional the compositional range of this beta phase is almost 100% silicon, very narrow range. If I zoom it, maybe it goes from 99.98 to 100% or something like that in the composition, okay. So that is fine. So this is so ideally you may have seen eutectics like this, or so I have told you that eutectics look like this, but this region which is the pure alpha phase now has become a very narrow region, right. So this has become very narrow, and similarly this region also has become very narrow, and this is a manifestation of the fact that gold does not like silicon, silicon does not like gold in the solid phase, right. So in the solid phase they hate each other, in the liquid phase they can combine with each other, right. So if I give them enough money, then they will say alright, let's stay together, enough entropy, that is, right. So enough money is entropy in my analogy, okay. Whereas in the low temperature phase they hate each other, they would segregate out into two different phases, and then so that is alpha here and that is beta here, that is pure alpha, pure gold and pure silicon, okay. Alright, so now once I start heating, this is gold plus liquid and this is silicon plus liquid, gold solid plus liquid, right. So once I start supplying more and more silicon, I am proceeding in this direction, and I am actually supplying silicon from silane, right. So, silane gets to gold and reacts with gold to form gold silicide, right, and gold silicide is formed in the form of a liquid, right. So, initially what I am doing is, let us keep these annotations. So, I am sending in silicon in the form of silicon H4, right. So, to gold, and this is going to form gold silicide, right. So, gold particle is going to convert into liquid gold silicide plus pure gold, right. So, I will have a phase mixture in this particle, right. So, part of it is just liquid, okay, let me just see, okay, part of this is liquid, maybe the outer part is liquid, let us say gold silicon, and the inner part is pure gold solid, right. So, this is, I am just guessing that the outer part is liquid, right. So, outer part, liquefaction typically starts from the surface, okay. So, this is a liquid, right. Alright. So, now I have an interface, I have a vapor which is silicon H4 which is reacting with a liquid gold silicide, right. So, this is the liquid, right. So, I have a vapor liquid interface at which silicon hydride is reacting with gold to form silicon gold alloy in the liquid phase, plus probably there is some evolution of hydrogen gas, right. So, that time I am going to take it away with my vacuum system, alright. So, this is what is going to happen. So, but this happens at the liquid vapor interface, okay, alright. So, now in the silicon gold, so as I keep on increasing my flux, right. So, the flux keeps on increasing. So, I am coming in this arrow direction. So, I am actually moving along this direction now. So, I am actually increasing in the liquid phase, I start increasing the composition of silicon, right. So, the composition of silicon in the liquid phase starts to increase, alright. Sorry, I start increasing the amount of liquid phase, right. So, not the composition of silicon in the liquid phase is here, right. So, this is the composition of silicon in liquid phase, this is the composition of gold in the solid phase, right. So, that is how I can read off the compositions, right. So, this is the liquidus, this is the solidus, right. But so by going in this direction I am increasing the percentage of gold silicide alloy, gold silicide liquid, right. So, that you can get from the lever rule, right. So, by traversing in this direction, right. So, I am increasing the liquid content in gold solid gold silicon liquid mixture, right, to such an extent that once I reach here, right. So, I keep on supplying more and more silicon, once I reach here, at this point it is 100% liquid gold silicon, right. I do not have any solid gold, it is 100% liquid gold silicon, okay. At this point it completely becomes, right. So, at this point it completely becomes a liquid gold silicon, 100%, okay. No solid gold anymore, right. So, all gold has converted to liquid, but it is an impure liquid, right. So, all the gold has converted, let me write it down so that I am writing down things so that I emphasize it more, I can just say things and then relax, but all the gold converts to liquid gold, right, at this point, right. Let us read that composition as X star, at X star to liquid not gold, but gold silicon alloy, right. It is an impure alloy, gold should be contaminated with silicon, right. Now, if I have to melt gold, I have to melt gold here at this temperature 1064 degrees Celsius, right, but I am doing this reaction at 800 degrees Celsius and I am still able to melt gold, but by adding impurities, right. So, at 800 degrees Celsius, I have to add X star amount of silicon in gold so that the gold nanoparticle melts. Okay, all right. So I have melted the gold nanoparticle. Okay, so by here I have 100%, you know, at X star I have 100% liquid. Okay, right. So now I have a particle, I have a liquid droplet at X star, right. So with X star you know, composition of silicon, and this is 100% liquid from the lever rule, right, and you know, still there is vapor of silicon coming. Okay. Now what happens? Let us go back to the phase diagram, right. So still I am proceeding in this direction. Oops, sorry. I am still proceeding in this direction. Okay, so let me change the color now, so that in color is, let us say, this color. I am still proceeding in this direction. Okay, and now, you know, so the phase coexistence now is AuSi liquid plus silicon solid. This is what I want, right. So I am now going to precipitate out silicon solid. What is the composition of silicon solid that I am going to precipitate? 100%, right. So the solidus line of silicon is here, almost 100% silicon, right, and the liquidus line is here. So gold silicon has this composition, that is okay, but it starts to precipitate out more and more silicon, solid silicon, right. So at X star, just slightly larger than X star. Okay, so at X slightly greater than X star, I start precipitating pure silicon. Okay, now where is the silicon precipitated? I have a liquid gold, I have some silicon substrate, right. So typically the precipitation happens at the substrate, right. So at interfaces. Okay, so this is the liquid solid interface at which silicon precipitates. Okay, so this is the first nucleus of silicon that is formed, right, and then more and more silicon starts to get precipitated, more and more, you know, more layers of this is added to this droplet, and then, you know, so eventually the droplet is just finite size, so the droplet starts to rise. Okay, so I have a silicon that is precipitated, and you know, more and more silicon starts falling on this interface from the gold. So if it has to precipitate, it precipitates here. So the length of silicon just increases, it's just in this direction, right, and the gold droplet starts to, you know, rise up, right. So the gold droplet is rising up. Okay, so eventually I will get a nanowire, which is a single crystalline nanowire, right, with gold droplet on the top, right. So once it has grown to some 10 microns or whatever it is, and the size of the nanowire is determined by gold size, and gold size can be, you know, 10 nanometers or 2 nanometers, whatever it is. I can make it small. If I control the size of the gold, I can make the nanowire size also small, right. So I can grow really large aspect ratio nanowires, right. So large aspect ratio single crystalline nanowires, these are all single crystalline, because, you know, so I have one nucleation event, and then there is growth, more growth on that, you know, I just have again we will talk about nucleation growth, but I have, you know, so one silicon that is a chunk of silicon that comes up, nucleates, that is a single crystal, the first nucleus is a single crystal, but more and more add atoms come and attach to it, more and more silicon precipitates come and attach to it, just extending these planes, right. So more or less you get always a single crystalline nanowire. Okay, and the single crystalline nanowire, the aspect ratios, if I am talking about it, I can have aspect ratios of something like 10 microns to 10 nanometers. This is huge, right. So 1000, right. So I can really grow long nanowires of silicon, right. So these are actually 1D structures in our definition of, dimensionality that we started with this course, right. So this is how you start growing this 1D structures of nanowires. Okay, so if I look at the final morphology, and then so more and more silicon keeps getting precipitated as I keep going along, and then at some point you should stop the process. Once I have enough length of the nanowire, I will stop the process. Okay, and as you can see from the microstructure, right. So this is the length of the nanowire. If you look at maybe I just wrote over it. That's fine, but let me just take this a bit here. Yeah, so if I just look at the length, the scale bar here, the scale bar is about 500 nanometers, right. So if I count, if I look at how long this nanowire is, this is the nanowire, right. This is something like 10 micron, I would guess, right. So you can just count how much, or even more probably, right. And how thick is the nanowire? This is very small, right. So in thickness, right. So maybe 20 nanometers, 30 nanometers or something like that, right. You can actually see the crystal structure of this nanowire, right. I don't think this is some indium arsenide nanowire, it's not silicon, right. So you can see the indium peaks and arsenic peaks. So this is indium arsenide nanowires, and these are important. Indium arsenide is good for making quantum dots and things like that. So but indium arsenide in itself is a very nice optoelectronic material, so I can make nanowires of indium arsenide, and then you can see that this nanowire terminates with the gold catalyst, right. So I can ignore this, I can make my devices away from the gold catalyst, and I can probe these nanowires, right. So a simple eutectic, right, simple gold silicon eutectic, I can use it to create gold nanowires, to create silicon nanowires. But the most important thing is I am doing this at low temperature, at a temperature which is less than the melting point of silicon, at a temperature which is less than the melting point of gold, right. So it's a low temperature processing technique, easy technique just to grow these single crystalline nanowires, and easy to set up also. All I need is a furnace, right. So if you really want to start your research, I would say start, and I don't always need these the precursors such as silane are also, you have to take a lot of, you should use them safely, right. But I don't need to worry about it. If I just want to grow indium arsenide or something else, I can just use solid precursors, and these solid precursors, right. So instead of using silane, which is a gaseous precursor, I can also use solid precursors, right. So for example, I am growing a material called germanium telluride, right. So which is what is called a phase change material. Maybe we did some overview of what a phase change material is. I will take a boat here, and in the boat I will put solid powder of germanium telluride, right. So I will heat it to a higher temperature. I will use what is called a 2-zone furnace or a 3-zone furnace, right. So this is heated to something like 800 degrees Celsius, whereas I will put my substrate on the downstream. This is the substrate with gold, right. So this here it is, so at 800 degrees Celsius, germanium telluride solid sublimates to give germanium telluride vapors, right. So that's the simplest reaction that I will use. Maybe not completely, but then I will have some vapor pressure, right. So it is not a complete sublimation temperature, but I will have some vapor pressure of germanium telluride vapor, and I am going to flow some argon gas, or this is called the carrier gas, right. And this carrier gas is going to fly my vapor above the precursor all the way onto my substrate, right. So the carrier gas carries my vapor to the substrate, okay. And so I have to control the carrier gas, okay. So again let me draw a furnace. This is a 2-zone furnace, right. So here I heat to temperature, high temperature, here I keep it at slightly lower temperature. This is where my VLS is happening. This is the substrate, this is the precursor, solid precursor, right. So this is connected to a vacuum pump and a control system, right, to control the pressure, right. Here is a furnace, right. So a coil furnace, right. So I will this is a furnace, but the furnace has a thermocouple. So control system so gets its thing from the pressure gauge, gets its signal from the pressure gauge. Here thermocouple measures the temperature, and from the temperature I can also design a control system to precisely set the temperatures, set and control temperature, right. And then I said we will flow some argon gas, right. So I have to connect this to some argon gas cylinder, bring the argon gas, right. So this is argon cylinder, and I flow it, right. So I flow the argon gas. So that is what is called my carrier gas. So I have to control the flow rate of the carrier gas. And that flow rate is controlled by what is called mass flow controller, MFC, right. So mass flow controllers. Okay, so just check out, so I have certain different controls, right. So I have pressure control, I have mass flow control, I have temperature control, right. With this 3 I can actually design a VLS system. The rest is thermodynamics, optimizing what this T low is, where the growth happens, optimizing this T high, right. So optimizing T low and T high, where growth VLS occurs, and T high where solid or solid precursor sublimates, has good vapor pressure. It does not need to sublimate completely, but it has a good vapor pressure, right, that the carrier gas can take it away from there and then put it on the substrate. Okay. So this is a simple process. If you have a simple lab with a furnace, you can set up this process, right. So and then start growing nanowires of various different semiconductors, right. So various different materials. All right. So let us so this is a short class. Let us just with this case study of growing nanowires, let us end this class here. So this is the a case study that clearly illustrates how a eutectic is useful, right. And you can design a simple process, right. So in the furnace that you have in the lab, if you have a mass flow controller, if you have a pressure controller, and if you have so of course with the furnace comes the temperature control, you can do this process at a fixed temperature, right, of the substrate and fixed temperature of the precursor, and then what results are actually nanowires, right. So maybe there are other types of growth also that happens. If you do it practically, you will see that it is not just the nanowires, but you get other forms of nanostructures also that do not require this catalyst, right. So they also compete with the formation of nanowires, but so you will get a few nanowires that you can use for your research, right. So that is fine. Okay. And in fact, so VLS was pitched. It's a bottom up way of making nanowires, right. So I am growing layer by layer, of these crystals, single crystals, right. And these are single crystals, so they should be, they should have higher mobilities and things like that, right. And so initially, so when the VLS research started in 2000s, people were of the opinion that so maybe you have to scale this up such that it can replace so how do you make nanowires typically? Typically I take a silicon wafer and then I start etching out, I start removing a lot of material so that I get some kind of a nano pillar or nano wire, right. So now it's like I'm burning out a lot of material, right. So that's the top down approach to make these nanowires, right. But instead of etching and then so I have, by etching I'm damaging the surfaces and other things, why can't I do it in a nice catalytic chemistry assisted, material science assisted way by using the phase diagram, by using the eutectic phase diagram. That was the idea at that point, right. And then people were able to make these nice silicon nanowires. It's another thing that to scale it to such large extent, etching based techniques are scalable, whereas VLS turned out to be not as useful and not as scalable in the current CMOS architectures that we use, right. So but it is still a very powerful technique to grow nanowires. Now how to use it in technology is still a problem, an open problem that one can solve, but so you can do a lot of beautiful science with these single crystalline nanowires, right. So, I have these 1D structures, I can control the size of these 1D structures, I can see effects of dimensionality, I can see a lot of other things, right. So, you just need to be imaginative and creative to create research problems out of these nanowire model systems. These help you as model systems, okay. So, in lot of research, okay. All right. So, with that let us conclude this class, and we'll meet again in the next class with a couple more phase diagrams, okay. And then and their advantages, and then we will end the discussion on phase diagrams, okay. All right. Thank you very much.